Good morning or afternoon, everyone. Today I will talk about our ICRA paper, DeFlow, Decoder of SymFlow Network in autonomous driving, the first rank method in ICRA'24 SymFlow online leaderboard. SymFlow estimation, which determines the 3D motion field of a scene, is essential in the field of autonomous driving. Such processing estimation in point level enhance downstream tasks like detection, segmentation, tracking, and occupancy flow. Most of methods in object registration SymFlow focus on relatively small scale point cloud data like ShapeNet and flying thing 3D. When they use point cloud data in autonomous driving, the points are downsampled to a size of 8,000 points or less. Most of methods fail due to memory overflow on modern driving dataset with the full number of points as input. Datasets like ICRA'24 and Waymo, where the number of points in one frame is around 80,000 to 117,000 points per frame. Existing work still have gaps either too slow, like NSAP on this large points input, which utilize multi-layer perceptions to refine the flow, leveraging the chamfer distance as matrix or loss. This figure shows how they use MLPs to optimize the model prediction. It does not learn any weight for the model, but optimize from start with new point cloud input. With thousands of iteration to get one scan frame flow, when n is really large, we need around 30 seconds, which do not satisfy our real-time running in autonomous driving. To solve that, recent researcher proposed voxel-based method for faster inference. For example, we directly transfer from endpoints to a fixed size to 2D grid or BV map or 3D voxel. The famous encoder is point pillar from 3D detection field. However, there is distinct difference between detection and SymFlow task. The later necessary point level result. Voxel-based methods often fail to realize the importance of the decoder designed in SymFlow task, resulting in their inability to differentiate features among points contained within the same voxel. This is because all points within a given voxel inherit the same features from the convolutional network. More specifically, existing methods set up resolution to 20 centimeter normally, where this histogram show all dynamic points moving distant inside 0.1 seconds. As we can see, the dynamic points are densely distributed within 20 centimeters moving distant. So existing voxel-based method performance decreased a lot on dynamic points, since the voxelization process often results in the loss of point-specific features. And our paper introduced DeFlow, which enabled transition from voxel-based features to point features using gate recurrent unit refinement. ZT here serves as an update gate. It takes the point features as input from here and utilize then which subsequently undergoes processing via 1D convolutional layers and utilize a sigmoid active functions. And T-1 here represents a previous hidden state. For the initial instance, H0 is set as M vector from the output of the unit. In our experiment, the number of iterations set as 4. And in our paper, we also formulate a loss function to address data imbalance on dynamic and static points. Time for experiment. Here are quantitative results. First, we achieve the sought performance in the online leaderboard compared the recent methods. The most significantly enhancement is observed in the boost accuracy of dynamic point flow estimation. As you can see, the endpoint error in foreground dynamic is the smallest in the table, with only minimal errors occurring in static points like 3 millimeters here and 2 centimeters here. Step into more detailed ablation in each module. This table on decoder with different resolutions demonstrates that our network have better performance and efficiency compared to the baseline. Here we use 20 centimeters resolution, achieve better performance compared with baseline who use 10 centimeters resolution. And we save 2 times GPU memories as GM in the table here, 6.3 GB vs 2.8 GB, and faster 2 times than baseline. And here are quality result in DeFlow. The color wheel means different colors represent different directions. With more saturated color indicate higher velocity here. As highlighted in the 2 green circle here, our DeFlow method demonstrates better performance in predicting motion angle and speed compared to FastFlow 3D. And conclusion. We introduced DeFlow, an efficient and high-performance method for autonomous driving in large-scale point clouds. It enhanced the extraction and reconstruction from point voxel point network features and a novel loss function in the paper. Our DeFlow ranks first in Argoverse 2 SimFlow online leaderboard. Future work is already under review now. A self-supervised pipeline using traditional dynamic awareness mapping as a prior to do self-supervise. And that's all about DeFlow. Please stay tuned with us. And if you want to run the experiment, check our code or scan here. Thank you very much.